Okay, so let's keep looking at some examples for finding the volume. So this first one, let's find the volume of the solid formed by revolving the region between y squared equals x and x equals 2y about the y-axis. So as always, our first step should be to sketch this function out. So here's my x and y axes. And I know I've got the line x equals 2y, which is just an equation that's the same as saying y equals 1/2 x, right? So for we start at the origin and we go up 1 and over 2. And so we get that line. And then we have the line y squared equals x, which is the same thing as the square root of x. And so we end up with this graph. So I'm going to zoom in a little bit to make it just a little bit easier to see. So we've got y squared equals x, and we have x equals 2y. And we're revolving this around the y-axis. So if we think about our slices, we need to integrate with respect to y. So looking at this shape, so since this is our region in here that I'm coloring in blue, we know we're going to have a washer, which means that we need two separate radii. So we need that bigger radius and the smaller radius. So our bigger radius is going to be the one furthest away from our axis of rotation. So I'm going to call that R. So we know R of y in this case, since we're integrating with respect to y, is just going to be the value of this linear equation minus our axis of rotation. So it's going to be 2y minus 0, which is just 2y. And then our little y, which is going to be our distance, our shorter distance, is going to be the distance from this curve, y squared equals x, back to our axis of rotation. So it's just going to be y squared minus 0, which is y squared. So now we have the information for our radii. We need our points of intersection, so we know what our boundaries are going to be. So we set the two equations equal to each other. So y squared equals 2y. Y squared minus 2y equals to 0. Factor out our y, so we get y times y minus 2 equals 0. So we get y equals 0. Y equals 2. And those ordered pairs end up being 0, 0, and 2, 4. Or sorry, 4, 2. All right. So we have y equals 0, y equaling 2. So now we're ready to find our volume. So remember the formula for volume. Volume is equal to pi integral from c to d big R of y squared minus little r of y squared for washers. And all of that's dy, since we're integrating with respect to a vertical line or vertical axis of rotation. So subbing in everything we know, this ends up being the volume is equal to pi integral from 0 to 2 of our big radius, which was 2y squared, minus our little radius, which is just y squared, dy. So it's pi integral 0 to 2, 4y squared minus y to the 4th dy. So we integrate this and we get pi times 4/3 y cubed minus 1/5 y to the 5th. And that's being evaluated from 0 to 2. And so then subbing in using the fundamental theorem of calculus and simplifying, you end up getting 64 pi over 15 units cubed for that volume. Alright, so let's look at this second one. So we want to find the volume obtained by revolving the region bounded by y squared equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So same thing. We start out by sketching our region so that we know what it's going to look like. So here's my x-axis, my y-axis. And so if we draw in what our regions are, right? So we know we're bounded by y equals x squared plus 1. So I'm going to label this every 2. Just to make it a little bit bigger. And so if I sketch this parabola, I know I would have 0, 1, and then I would have 1, 2, and then I would have 2, 5, which would be off of my curve. So it's going to look something like this for that parabola. So y equals x squared plus 1. We also know we're bounded by the lines y equaling 0, which is, of course, our x-axis. We're bounded by x equaling 0, which is the y-axis. And we're bounded by the line x equals 1. So our region we're looking at is this region in here. So the first thing we need to figure out is which variable do we want to integrate it with respect to. So we need to look at our axis of rotation. So here we're rotating it around the y-axis, which means we need to then integrate with respect to y. Now this places a couple of challenges on us, right? Because if we're going to integrate this region with respect to y, well, we have a problem. We have our functions changing, right? So if we look at this point of intersection, 0, 1, then our radii are changing, right? We're changing from, we have a disk down here, but then we have just a washer up here at the top part. And so that means we're going to have to do two separate integrals. So I'm going to call these two separate regions. I'm going to call this lower region R1, and I'm going to call the upper region R2, since we know we have two separate regions. And then we need to, so let's deal with each one separately, right? So we know our total volume is just going to be the sum of the two volumes. So if we look at region 1, this is going to be our simpler case because R1 is going to be a disk. So that means we only have one radius. So our radius for R1 is just going to be the distance 1 minus 0. Which is 1. Now if we look at R2, that's going to be a washer, which means we're going to need two separate radii. So for R2, we're going to have our big radius, so call this big R of y. And so that's going to be 1 minus 0 also, which is 1. But then we also have that smaller radius, little r of y, to take off that gap that we have. And so that's going to be our parabola. But the problem is, right, remember we're defining these in terms of y. But we have y equals x squared plus 1. So we need to solve this for x. And so when you do that, you get x is equal to the square root of y minus 1. And we know it's the positive square root because we're in quadrant 1. So both x and y's are positive. So our r of y then is square root of y minus 1 minus our other edge, which is 0, the y-axis again. And that just gives us the square root of y minus 1. So now if we put all of that together, so our volume, and I can actually pull the pi out of both pieces. So it's going to be pi times the integral from 0. So down here at the bottom, we're going from 0 to this point of intersection of 1. And then we know this other point of intersection is going to be 1, 2. So the first one goes from 0 to 1 of just our disk's radius, so 1 squared dy, plus now the second region. So this is R1. And then for R2, it runs from y equaling 1 to y equaling 2 of our difference of radii squared, right? So 1 squared minus square root of y minus 1 squared dy. So that's the volume for R2 once we take that pi into account. So we end up with pi times the integral 0 to 1 of 1 dy plus the integral from 1 to 2 of 1 minus y minus 1. So 1 minus y plus 1 dy. And then, of course, 1 plus 1 is just 2. So I end up with the integral of 2 minus y dy. So now it's just integration. So it's just the integral of pi, or equals pi times the antiderivative of 1 is y, evaluated from 0 to 1, plus two y minus 1/2 y squared, evaluated from 1 to 2. And so we do that. So plugging in, we have 1 minus 0 plus 4 minus 2 minus 2 plus 1/2. And so when we do that, we end up with 3 pi over 2 units cubed for the volume. Alright, so our next one's a little bit different. So we want to verify that the formula for the volume of a sphere is volume equals 4/3 pi r cubed. So to do this, we can think of a sphere as being nothing more, and I'm centering the sphere at the origin just to make my life easier. But really, a sphere is nothing more than a semicircle rotated around the x-axis. So if I think of this, I can just give this the generic sphere equation, x squared plus y squared equals r squared. Or for the positive side of this sphere, since we know we're going to want to solve this for either x or y, I'm going to solve it for y in terms of x, because I want to integrate this from negative r to r. If you think about this being centered at the origin, going in the positive x direction, that would be your positive radius. Going in the negative direction, that's your negative radius. So since I'm going to integrate this with respect to x, just to make my life a little simpler, then I'm going to solve this equation for y. So y equals the square root of r squared minus x squared, and positive square root because we're in the quadrant 1 and 2 region. So then our volume is going to definitely be a disk. And so it's any general x value. Our radius is our equation. Y equals x square root of r squared minus x squared. So then volume is the integral from negative r to r of pi times our radius squared. So square root of y squared or square root of x squared, r squared minus x squared dx. So this is pi times the integral from negative r to r of r squared minus x squared dx. Now it's worth mentioning, since we're looking at a sphere here, or a semicircle basically, we could use the symmetry of this to our advantage and just make this 2 pi integral from 0 to r to make our life a little bit easier. It doesn't matter, so you could do this. And just say it's 2 times the volume for the region of everything from the origin over to the radius. I'll do it both ways just so you can see you'll get the same answer. But so it really doesn't matter. It's just whether or not you would rather have to deal with r's and negative r's, or if you would have to deal with zeros and r's. So I'll do it first using the negative r to r. So that's pi times my antiderivative of r squared minus x squared with respect to x is r squared x minus 1/3 x cubed. And that's going to be evaluated from negative r to r. So that's pi times, when I plug in r, I get r cubed minus 1/3 r cubed. When I plug in negative r, so minus a negative r cubed, which then just becomes plus r cubed. And then minus a negative, which is plus 1/3 x cubed, but this is negative r, so that's going to then be minus again. So minus 1/3 r cubed. And then we're just combining, so I've got 2r cubed minus 2/3 r cubed. And so then, of course, 2r cubed, that's going to put this over a common denominator of 3. It's going to be 6r cubed over 3, or 6/3 r cubed minus 2/3 r cubed times pi, which then gives us our volume formula, which is pi, in this case, the way I've got it written, pi times 4/3 r cubed. I'm just going to rewrite it in our standard form, 4/3 pi r cubed, since we can multiply in any order. And it's still units cubed. Now, if I were to do this the other way, so we know that these are equivalent. So that's 2 pi times, when we to find the antiderivative, r squared minus x squared, that's still going to be r squared x minus 1/3 x cubed. Now it's just being evaluated from 0 to r. So that's 2 pi times, plugging in r now, r cubed minus 1/3 r cubed. So I get 2 pi times, so same thing, 3/3 r cubed minus 1/3 gives me 2/3 r cubed, and now 2 times 2/3, that is 4/3. So 4/3 pi r cubed. And so you get the same result using either the symmetry or just brute force negative r to r. So you get the same thing either way. So one that's a little similar but a good real-world application. So a manufacturer drills a hole through the center of a metal sphere of radius 25 inches. The hole has a radius of 7 inches. We want to know what is the volume of the resulting ring. So same idea, right? Let's sketch it out. So here we've got our sphere that has a radius of 25 inches. So we know we're out here at 25, negative 25. This is going to be 25. And our equation of that sphere is x squared plus y squared equals 625. Because remember, the equation of a circle is x squared plus y squared equals r squared. And we're drilling a hole through here, through the center, with a radius of 7 inches. So that distance from the origin to the x-axis is 7, or from the x-axis up to where we're removing. So this is coming out, has a radius of 7 inches. And we want to find the volume of that resulting piece that I'm going to shade in green. So we want to find the volume of this green region. So to do this, we're going to use a similar approach. So we know we're going to integrate from these 2 points of intersection here. And it's going to be a washer, if I think about this as rotating it still around the x-axis, just to make our life simple, and I'm still centering it at the origin. So it's going to be a washer because we're going to have that yellow piece that we're moving. So we're going to need the 2 radii, right? So this big radius is going to be from the outside of my sphere to my axis of rotation, which is the x-axis. And then so that's going to be my big R of x. And then I'll need the smaller radius, which is going to be what I'm taking out basically. So that's my little r of x. So we've got to find big R of x, little r of x, and our 2 points of intersection, which are going to be our A and our B. So let's find the points of intersection first. So we know we've got x squared plus y squared equals 625. We also know the other equation is y equals 7. because it's a horizontal line where our drill bit's going through at a height of 7 inches. So since we know y equals 7, we can just plug. You could solve this equation first for y, which we're going to need later anyways. So you could do this. Y equals the square root of 625 minus x squared. Again, positive square root. So you could set this and then set y equal to 7. So just plug in 7 for y that way. Set the two equations equal and solve. But an easier way to do that is, since we know y is 7, let's just plug into the x squared plus y squared equals 625. So x squared plus 7 squared equals 625. X squared plus 49 equals 625. X squared equals 576. So then x equals plus or minus 24. So we know these intersect at 24, 7 and negative 24, 7. So if we set this integral up, well, we need our radii. So big R of x, that's just going to be my outside of my sphere, which is square root of 625 minus x squared, minus my axis of rotation, which is 0. So that just ends up being square root of 625 minus x squared. And my little r of x is basically the distance that my drill bit's going to remove. So 7 minus 0, which is 7. So now the volume, I can set it up the full formula. So volume equals pi integral negative 24 to 24 of my radius, which is big radius, square root of 625 minus x squared squared, minus my little radius of 7 squared dy. And so I get pi integral negative 24 to 24, 625 minus x squared minus 49 dy, or 576 minus x squared. Dy when I combine that 625 and negative 49. You could also use symmetry to your advantage again. In this case, since it's negative 24 and 24, I'm not going to use symmetry. But you could set this up as 2 pi. So 2 times the integral of pi 0 to 24 of that 576 minus x squared. Sorry, not squared, just 6. So you could just leave this as 570 as the 2 pi times the integral of from 0 to 24 of 576 minus x squared. Or you can leave it as negative 24 to 24. And so then I'm just going to leave it. And so if I integrate this, that's pi times 576x minus 1/3 x cubed, evaluated from negative 24 to 24. Subbing in, I end up with pi times 13,824 minus 4,608 when I plug in positive 24. And then when I do the negative, so minus a negative becomes plus 13,824 again. And then minus a negative, but then with a negative in that, ends up being minus again 4,608. And so combining all of that, I end up with 18,432 pi units cubed. Or sorry, inches cubed, because we actually have our inches here. we have the units cubed. And you should get the same result if you do that as 2 times the integral from 0 to 24.